have learned so far about the three physical quantities which we can use to describe motion. Okay, the first one is displacement, then we learn about velocity, and in the last lecture we learn about acceleration. So in this lecture we will learn how to derive a relation between these three physical quantities, and we'll derive the relation among these three physical quantities for a uniformly accelerated motion, and by using a graphical method. So here we consider a uniformly accelerated motion, and the velocity time graph for the uniformly accelerated motion is shown in the figure. So here at time t is equal to 0, the velocity is v0, and after time t the velocity of the object is v. So here we have the initial velocity v0 and the final velocity v, and since it is a uniformly accelerated motion, the velocity time graph is a straight line. So now we'll derive the first equation of motion. Now from the definition of acceleration, okay, so we'll derive the first equation of motion. So from the definition of acceleration, your acceleration this average acceleration is equal to the change in velocity, which is v minus v0, divided by the time interval, which is t minus 0. So here A is equal to v minus v0 divided by t, and here by cross multiplication we'll have at. This is equal to v minus v0. So we can write this as v. If I bring this one this side, you'll have v to be equal to v0 plus at. So this is the first equation of motion. This will give us the final velocity of the object after a time t, okay, moving with a uniform acceleration a, okay, starting with the initial velocity v0. So this is the first equation of motion. So you can write this as equation 1. Now we shall derive the second equation of motion. Now we recall from the last lecture, if we have a velocity time graph, then the area under the velocity time curve will give us the displacement of the object over the given time interval. So here we have velocity time curve AB, and the area under this AB, that is OABD, area OABD will give us the displacement. So here the displacement denoted by x is the area under the velocity time graph, which is area OABD. So this will give us the displacement, the area OABD. Now area OABD, from the diagram we can see that the area OABD is equal to area of the rectangle OACD plus the area of the triangle ABC. So this will give us the displacement of the object in the time interval t. So here your displacement x, this will be equal to, now area OACD. Now to calculate the area of the rectangle, we have V0 OA into OD, and OA is equal to V0 and OD is equal to T. So from the diagram, area OACD, this is OA, side OA into side OD, and area of the triangle, this is half base, which is AC, into height, which is BC. And OA from the diagram is V0 and OD from the diagram is T. So we have V0 T, then plus half. Now area of the triangle is half AC into BC. Now AC from the diagram is T, and BC from the diagram, we can see that BD is equal to V and DC is equal to V0. So BC will be equal to BD minus DC, and that is equal to V minus V0. V minus V0. So this will be the displacement V0 T plus half T V minus V0. But if you can recall from equation 1, from the first equation of motion, we have V is equal to V0 plus AT. So from the first equation of motion, we have so from equation 1, what we have is V to be equal to V0 plus AT, and if I bring this one this side, I'll get V minus V0 to be equal to AT. So this is from the first equation of motion. So V minus V0 is equal to AT. So here if I keep this one here, instead of V minus V0, I'll write AT. So I'll get T into T will be T square. Hence I'll get the displacement to be equal to V0 T plus half AT square. So this is the second equation of motion. Okay, I'll write it here. AT square. So this is known as the second equation of motion. So this gives us the relation between displacement, the initial velocity, acceleration, okay, with respect to the time. Then the third equation of motion. Now in the third equation of motion, we shall relate the velocity, the acceleration, and the displacement. So again, we know that the displacement is equal to V0 T plus half v minus v naught t. This is the area of the rectangle OACD. This is the area of the triangle ABC. So what I'll do now is I'll open the bracket. So I'll get, opening the bracket, I'll have half VT minus half V naught T. Then we have here V naught T minus half V naught T. So 1 V naught T minus half. So 1 minus half will give us half. So what we'll have here is half Vt, 1 minus half will give us half V naught T. Then you can take common half and T again. So we'll get half V plus V naught into T. So here what we'll have to do is we'll have to eliminate this T. So we have the displacement to be in terms of velocity and time. We want to get the relation between the displacement, the velocity, and the acceleration. So here we'll eliminate this T. And again, from the first equation of motion, what we have, so from equation 1 again, so from I'll write it here. So from 1, what do you have? V is equal to V naught plus AT. So if I bring this one to the side, this will give me V minus V naught equal to AT. And again, upon cross multiplication, I'll get T. So this is upon cross multiplication. T will be equal to V minus V naught divided by A. So instead of this T here, I'll write this. So your T, I'll write with this one, will be V minus V naught divided by A. So here we have half V plus V naught into V minus V naught divided by A, and this is the formula. You can use the mathematical formula. A plus B into A minus B will give you A square minus B square. So here V plus V naught into V minus V naught, this will give you V square minus V naught square divided by 2A. So this is the displacement x, and again you can bring this one here. So you will get 2ax. So here your 2ax will be equal to v square minus v naught square. So this is the third equation of motion. I'll write it here. V square minus v naught square. So this is the third equation of motion. It relates the acceleration, the displacement, and the final velocity and the initial velocity. So these equations are valid for a uniformly accelerated motion. For example, an object falling under gravity. We can use these equations to solve problems which relates to object falling under the effect of gravity. So these are the three equations of motion. And the first equation is V is equal to V naught plus AT. Second equation is x is equal to v naught t plus half a t square, and the third equation is v square minus v naught square to be equal to 2ax. So these equations, okay, we have derived them by assuming that the initial position of the object is at 0. That is, when the time is equal to 0, the position is equal to 0. And when the time is equal to t, the position is equal to x. But if your initial position is non-zero, that is, if at t is equal to 0, suppose you have at t is equal to 0, the position is non-zero, say it's equal to x naught, then there will be a slight change in the above equations. So if at t is equal to 0, the position is equal to x naught, then we'll have to add, instead of just x, we'll have to add this x minus x naught. So this will give us the change in displacement. So here, instead of this x, I'll have to put x minus x naught. Instead of this x, I'll have to put x minus x naught. X naught is the initial position, x is the final position. So that will give us the displacement. Again, let us recall the displacement is the change in position. So here, instead of x, I'll put x minus x naught. So if the initial position is x naught, the displacement will be x minus x naught. Final position minus initial position is equal to v naught t plus half at square. And here also we have v square minus v naught square. This is equal to 2a. The displacement will be final position minus the initial position. So this is when the initial position is non-zero. In these two cases, the initial position is assumed to be 0, and in these two cases, the initial position is x naught.